So, okay. Good morning to everyone. Yeah, today we'll start operational amplifiers. Okay, so operational amplifier, what is the importance of the operational amplifier and how you can design the operational amplifier and what are the different types of operational amplifiers? Okay, the syllabus of this module, particularly this module, is general considerations, performance parameters, one stage op amp, two stage op amp, gain boosting circuit, next comparison, common mode feedback, input range limitations, slew rate, power supply rejection. So these are the topics which we can cover in this module. Yes. Okay, we'll start with the basics. Op amps are the integral part of many analog and mixed signal systems. Yes, the basic building blocks of many analog and so mixed signal systems is the op amp. So op amps are having many ideal characteristics which are very suitable for the different applications. 1 minute. Yeah, op amps are the integral part of many analog and mixed signal systems. As I told you, op amp has many ideal characteristics which are suitable for many applications. So as we discussed earlier, we have different devices, generally active elements, active devices, MOSFET and transistor. These are the active elements, active devices. So op amp also active devices. Okay, so these active devices or active sources or active circuits are plays very important role in the, so especially in electronic circuits. So we have different types of op amps. So as I told you, the basic op amp characteristics are very tempting for the many applications because we have I think wide gain, large gain, wide bandwidth, zero drifts. Okay, so higher input impedance, low output impedance. These are the primary requirements for any amplifier. So generally, when we discussed about BZT and MOSFET will have some benefits and BZT will have some benefits. So, but we need both the advantages combination of together. Okay, together both the advantages, so that we can find them in the op amp. Okay, so anyhow, op amp is the basic element in many analog and so mixed signal systems. Okay, next, op amps with so different levels of complexity are used to realize functions ranging from DC bias generation to high speed amplification or filtering. What is saying? So op amp, simple op amp and complex op amp. So depending on the application or depending on the requirement, the op amp complexity may be varies. So sometimes we can use a simple op amp. Sometimes we need the complex op amp. Complex means I think so 2 stage, 3 stages with some what is that one extra circuits for compensation something. So op amps have different levels of complexity based on the what the relation the functions. What functions we have? Sometimes we need to generate the biasing, sometimes high speed amplification, sometimes filtering. Based on the what? So the function required, the op amp complexity can be varied. The design of op-amps continues to pose a challenge as the supply voltage and transistor channel length scale down with each generation of the CMOS technology. Of course, so definitely op-amp has also, not only op-amp, of course, we studied that any VLSI circuit or any VLSI device or the VLSI circuit definitely it poses a challenge. So when it is designing at the latest technology node, because the same device should operate with the lesser voltage and same device dimensions are channel length modulations. So all the things will be plays a vital role. And when you are going to the downscaling, technology downscaling, definitely the same device, when you are designing at the device or the circuit designing at the same, that means latest technology node, so definitely it has it has many challenges. We have many challenges how to overcome them. So we will discuss with the analysis and design of the CMOS op-amps. So what is the analysis and what is the design procedure of the op-amp? So with the review of performance parameters, we'll describe the simple op-amps such as telescopic and folded cascode topologies. So simple op-amps. So op-amps, you have two different types of topologies. One is telescopic, one more is a folded cascode topologies that we will discuss. So with the performance parameters, what are the performance parameters we will discuss? So op-amp has many performance parameters which will be highlighted based on the application and requirement. Okay, so after that, after discussing about the simple op-amp configurations such as telescopic and folded cascode in terms of the performance parameters, so we will go for the two-stage op-amps, gain boosting configurations, and the problems associated with the common mode feedbacks. So after that, at the end of this module, we'll discuss the concept of the slew rate and analyze the effect of the supply rejection and the noise in the op-amps. So how to avoid the noises in the op-amp, that we will discuss at the end of this module. Okay, so these are the basic what is that one procedure what we are going to discuss in this especially module. In the op-amp module, we will discuss or we will learn how to design the op-amp and analysis of the op-amp. Analysis means frequency response finding. Okay, and moreover, simple op-amps with their performance parameters, how to highlight them. And so at the end of this module or at the end of this op-amp topics, we will discuss the slew rate, what is the importance of the slew rate, and supply rejection ratio, and how the noise, what type of noises are there, and how we can avoid the noise, how can we reduce the noise. Got my point? What are the things we can and we will discuss in the op-amp? Are you understanding? These things we will discuss.
Okay, sir.
Yes. So now come to the point. So has our definition, what is the op-amp definition? Because you are already crossed the UZ, so that you know op-amp is a high gain differential amplifier for which feedback is added to control the gain. That is the basic definition of the op-amp. Of course, everyone can describe their own definition, but the soul of the definition is this one only. It is high gain differential amplifier. High gain differential. You know the differential amplifier, higher gain. So differential amplifier plus higher gain. So that is the basic name. The feedback, generally feedback is added for the op-amp. Okay, so we have two configurations, open loop and closed loop. But closed loop will have some advantages. Like you know, the closed loop has you have a control. You can have a control over the gain. You can get the variable gain, not some particular value. So you can vary the wide range of gain from this much value to that much value. So generally, so that is the op-amp definition. You know, high gain differential amplifier. So the gain, high gain, what is the gain range? The gain range is so 10 to 10 lakhs. So 10 power 1 to, that is the order of 4 simply. So 10 power 1 to 10 power 4. This is the, so if you take the MOSFET, how much gain you will get? Can you tell me? MOSFET gain. Hello? And BZT gain. In MOSFET, the gain you will get in 100, tens only. In BJT, you will get the hundreds of gain. But in in the op amp, you have a what? 10 power 5. So that means 10 power by 5 means what? So 1000 K. Am I correct? Okay, 1000 K. So this is the higher gain. So this is the op amp basic. What is that one? Importance and basic. Why you are choosing the op amp means because of it is a higher gain, high gain amplifier. Okay, understand?
Sir.
10 power 5 and 10 in terms of kilo.
10 square into 10 cube kada.
10 power 5. Okay, understand. Okay. 100 K. Okay, then. So in the earlier, that means in olden days or couple of decades back, whatever the op amps we designed for to serve they serve as the voltage very high voltage gain amplifiers. So several hundred thousands of gain. Okay, so that is the main. And whatever the op amps which we designed, which we were designed earlier, so they have a what they can use for the purpose of they provided very high voltage gain, higher input impedance, and low output impedance at the cost of many other aspects of the performance. Yeah. So these are the things mainly we concentrated in the previous designs. What is that? More voltage gain, high input impedance, and low output impedance. These are the basic requirements of the op amp, of course. Operation amplifier or any amplifier, the basic requirements. At the same time, while you are going to design or improve the gain or the higher input impedance or to reduce the load, we are actually we were lost some parameters. What are the parameters we suffered when we are mainly concentrating on these three parameters? Means speed, output voltage swing, and power distribution. So at the cost of these three parameters, so the designs were, I think the designs were happened in the earlier. But now, everything is very crucial. So maybe in the earlier designs, the technology node may be not today's like it's maybe a 300 nanometers or 180 nanometers. So at that point of time, I think the power dissipation is minimal. It's low, so that we don't want, we were not what is that one much worried about that power dissipation like voltage things, because we took the large voltages. That means VDD values nearly 5 volts or more than 5 volts we used actually, so that the voltage swings are not much affected, and speed also. But they are actually the three performance parameters are affected. But at the higher technology node, the impact is very less. That's why we didn't bother about them. But now, what happened? Since the technology downscaling, now the technology node may be below 45 nanometers. So 10, 16, and 22, like that. Okay, the technology node is very small. At that time, the variation, the impact of these performance parameters, speed or voltage, output voltage swings, the power distribution is very high, because the device is scaling. Definitely, the power dissipation becomes very high, so that you cannot, you can't neglect now as earlier case. And similarly, you are using the lower voltages to operate the device. So I think if the output voltage swings are affected, then I think it's very difficult to survive get the output and speed also. Okay, so anyhow, you need to understand one particular point at this point. In the earlier designs of the op-amp, okay, they were concentrated only on the voltage gain, input impedance, output impedance. At that time, they affected three parameters: speed, voltage swing, and power dissipation. But the impact of them are not much at the higher technology nodes. But today, the technology is downscaling, and at most the technology node is at 7 nanometer. Okay, so these three impact is very high, so that today's designs must be different from the earlier designs. So that today op-amp design proceeds with the trade-off. Trade-off means, yes, if you need one thing, we need to compromise with the other, or to bring the optimum value between these three. So between the parameters required, multi-dimensional compromise in the overall implementation, making it necessary to know the adequate values that must be achieved for each parameter. Yes, the particular design procedure should be there, and we need how to compromise between the required parameters. So, or I think suppose if you want low power dissipation, then you need to compromise with the speed and the output voltage swing. Or if you want higher speed amplification, then you may be compromised with the swing and dissipation. So, but you have to, how much you can compromise at some extent only. So we need to bring the trade-offs between these parameters. So that is very important. So that today's designs are very challenging than the earlier designs. Because I told you one thing, in the earlier designs, the technology node is high, so that the effect is, of course, the effect is there, but it is not much more impacted. So on the application or the operation of the device or the circuit. But today, see, as because of technology downscaling and we're working at the low technology node, the impact of these things are very, very high. So that we have a more challenges to optimize or to bring the trade-off between the parameters. So understand? Hello?
Yes, sir.
Yes, sir.
Yeah, what is the difference between the earlier designs and today's what we are expecting today's designs? Today means you are the now you can design the op-amp. So at this time and whatever the technology node we are using, so in the laboratory, so definitely you have a, so you need to bring the trade-off between the parameters. You cannot you can't say that I don't bother about the speed or I don't bother about the power dissipation. Yeah, because the magnitude or the quantities of these are suffering is very, very high. Okay, so if the speed is critical while the gain error is not, a topology is chosen that favor the former and possible sacrifice in the latter. So what he's saying, he is talking about the example. If the speed is critical, the speed and gain is talking about. If the speed is very important, at any cost, I need the higher speed. Application must be, or the application or the circuit operation must be very high speed. Then you need to compromise with the gain. Okay, so depending on the situation, you need to compromise with, but up to some extent only, so that the topology is chosen. So for that applications, what to do? So you need to choose the speed only. I think we must sacrifice the gain. Maybe you may not be get the whatever the gain earlier device. You are suffering. You are reducing some gain. Yeah, no, okay, no problem. So that is the thing. So that is called the optimization or the trade-offs. Here, what in between the two parameters we are going to the trade-off. We are bringing the trade-off. One is the speed. One more is the gain. So that is the this is purely application oriented. But earlier designs, whatever the op-amp you have, that can be fit for anything. But now it is not like that, because you are compromising with some parameters, some performances parameters, so that suppose when you are important, you need a very high important on the speed, then the rest of things you are not taking bother about them. So that this is not fit for the other things. Only it can be used for the higher speed of applications. Similarly, sometimes if you design the only higher gain and you are compromising with the speed and some other thing, then this is not useful for the this amplifier is not useful for the high speed application. It is useful for the high gain applications. Okay, are you okay? Yeah, I need the response. Yes.
Yes, sir.
Now we will talk about the performance parameters. Okay, this is the thing you know already. This is the cascode op-amp or cascode amplifier. So this is the differential pair, and these are the, so see, different pairs of transistors we take to cascaded transistors. For what purpose? These are the current sources, of course. Okay, for loading effect. So this configuration already we explained, we discussed in the last module. But now again I am taking this for explaining the parameters. So in this circuit, in this cascode amplifier, so differential cascode circuit, this is the voltages VB1, VB2, VB3. These are the what? Biasing voltages to make all these devices. This is to make these devices as okay as the current sources. These are also current sources. These are also current sources. Am I correct? So current mirror concept for applying the current mirror concept. So VB1 to VB3 voltages should be chosen in such a way they provide the constant current sources that can act as the current sources. Yeah. So later, op-amps of this type have, this cascode op-amps have high output impedance. High output impedance. Generally, our requirement is low output impedance, but they have us high output impedance because of this cascading structure. Sometimes they are called as OTAs. OTA means operational transconductance amplifiers. So what is the in the limit, the circuit can be represented by a single voltage dependent current source called GM stage. Yeah. So if you draw the equivalent circuit, okay, if you draw the equivalent circuit, then what happened? Because there are many transistors, but you can take with a one voltage dependent current source, okay, whose gain is GM, whose value is GM into something, GM into V in some V1 something like that. So that is the one more advantage. So what are the parameters we should consider for this circuit? So gain is one parameter, small signal bandwidth is another parameter, large signal behavior is another parameter, output swing, linearity, noise, and offset and supply rejections. These are the parameters which we want to discuss, okay, for an amplifier. Okay, this is only the cascode op-amp. Okay, this is an amplifier. So I am talking about the only parameters. What parameters we should be considered? So while designing an amplifier, so gain, small signal behavior, large signal behavior, and small signal bandwidth, output swing, linearity, noise, offset, and supply rejections. These are the main parameters which we should consider in the design of the amplifier. Got my point?
Yes,
I
sir.
hope you understand. Okay, this is what is the circuit? Cascode amplifier. Here, what is the M3, M4, M5, M6, M7, M8 will do? Will do as the current mirror concept. They introduce the current mirror concepts. Okay. So VB1, VB2, VB3 are the voltages which must be applied to M3 to M8 transistors to make every transistor in the saturation. Thereby, they act as the constant current sources. Do you agree with me?
Yes, sir.
Yes. So what is the because of this cascode structure, cascode structures have higher output impedance. That is the one thing. This type of amplifier is called the OTA, operational transconductance amplifier, because so high output impedance is there.
Sir,
And moreover,
final attendance.
one more thing. So what happened? So when we are going to draw the circuit of the circuit, equivalent circuit, small signal equivalent circuit. So all the M3 to M8 transistors are, so they can be replaced by a single voltage different current source
final
with
attendance
the
katna.
GM value, with the GM steps. And moreover, for this circuit,
అదే
we need to
పంపించమని
discuss
చెప్తున్నాను.
what is that one?
అటెండెన్స్ చేయాలంటే
The
అక్కడ
parameters. Which
డాక్యుమెంట్స్
parameters
ఉండాలి
we need
కదా.
to consider? Gain, small
లేదంటే
signal
మీరు
bandwidth,
వెళ్తారంటే
small signal
శాసింద్ర గారికి
behavior,
పంపిస్తాను.
output swing,
అయితే
linearity,
ఆవిడకి సెండ్
noise,
చేయండి.
and offset, and supply rejections. These are the parameters we should be considered. Okay. Next, what is the gain? We'll discuss. So, open loop gain of an amplifier, op-amp, determines the precision of the feedback system employing the op-amp.
మేడమే చేశారే.
So, gain of open loop gain and closed loop gain, these two things are there. Open loop gain of the op-amp will bring the precision, of the feedback system employing the op-amp. So what is the precision? Precision means what? Suppose if you take the one system whose gain is suppose 50.
ఏవి కూడా మీరే చేశారట కదా.
Okay, if the feedback is added, if the gain is required exactly, so 25.999. Okay, then so by the adding of this feedback, for this amplifier, you can bring this precision 25.999. High precision can be achieved by using the what? So by employing the feedback, you can get the high precision. So that is called the gain. The trade with the speed and output voltage swing, the minimum required gain must be therefore be known. Means to bring the trade-off between the speed and the output voltage swings, what is the minimum gain is required? That we need to know. So that is the importance of the gain. Okay. So one example is here. That is the one circuit is there. For that circuit, designed for the normal gain is 10, and 1 plus R1 by R2 value is 10. That is the normal gain. Determine the minimum value of A1 for a gain error is of 1%. To have a 1% of gain error, okay, then what is the minimum value of A1? Where A1 is the open loop gain. This is the op-amp. This is the op-amp amplifier circuit. What type of this circuit is this? Non-inverting amplifier. Non-inverting amplifier. Okay, here A1 is the open loop gain. A1 is the open loop gain. So what is the closed loop gain formula? Gain means what? Output by input. Gain means what? Output by input. It is the ratio of output voltage to the input voltage. So generally we have a because of it is a non-inverting amplifier. You know, it is a basic thing. So that I don't want to share the analysis. Just I will write the is transfer function or the gain, closed loop gain. Closed loop gain is equal to, what is the closed loop gain formula? So V out to V in. Formula is equal to A1 by open loop gain by 1 plus feedback factor is multiplied with the open loop gain A1, where beta is equal to feedback factor. It is nothing but 1 plus, so R2 by R1. This is the beta value. So otherwise we know that V out is equal to, here if you do the analysis, then V out is equal to, in terms of V in, V out is equal to 1 plus R2 by R1 is multiplied with the V in, input voltage. That means input voltage is multiplied with this constant, then you will get the output. That is the, so output to input. So this is the closed loop gain formula. So what is that one? Open loop gain by 1 plus feedback factor is multiplied with the, so what is that one? Open loop gain. So that is equal to, I can write, that is equal to, what is the A1? Otherwise you can write the A1 as it is. Yeah, that I want to find. 1 plus beta values. What is the beta value? So R2 by, sorry, beta value is not this. This one only. You can write this like this. Beta values 3. So R2 by R1 plus R2. You can write like this. Okay. So now You can substitute this beta value R2 by R1 plus R2 is multiplied with the A1. So now you can divide the numerator and denominator with the R2 by R1 plus R2. Then you will get, so R1 plus R2 by R2 is multiplied with the A1 by so R2 plus R1 plus R2 by R2 plus A1. Yes, this is the thing. So what is saying in the circuit? The nominal gain is 10. That means 1 plus R1 by R2. That means R2 plus R1 plus R2 by R2 is 10. So what is saying? A1 should be greater than, far greater than 10 is saying. So that I can write this equation. This equation approximately equal to 1 plus R1 by R2 into 1 minus R1 plus R2 divide with R2 into A1. Okay, so here 1 plus R1 by R2 into A1 is the relative gain error here. So 1 plus R1 by R2, okay, so into A1. This term is called the relative gain error. Gain error. Yes. So what is saying? 1% of error. A1. What is the value of A1 for gain error of 1%? So for 1% of gain error, okay, means this is the A1 value. A1, this is the condition. A1 should be far greater than 0, far greater than 10. So that you can write for 1% of error, you can write this value as, yes, 1% of error means 1 by 100. 1 by 100 should be less than this factor. What is that one? This factor 1 plus R1 by R2 into A1. So this must be far greater than 10. With this, A1 should be greater than, because this value is 1%, 1% error. So that A1 should be far greater than, I think 10 is multiplied with 100 is 1000. This is. Hello? Hello? Understand this one? Understand?
Yes. Yes, sir.
Anyone have doubt?
ఒకసారి లాస్ట్ లో చెప్పండి 1/100 లెస్ దాన్ అక్కడ.
So this is the what? Relative gain error.
Relative
This
gain
error
error.
should be greater than, should be less than,
Relative
should be
gain.
less than. Enta? What is saying? This is
1
gain error.
plus.
So 1 plus R2 by R2, R1 by R2 into A1. Value should be less than 1%. 1% means 100. Ante kada? So then, what is the A1 value? A1 value is 10. So then, that means it should be greater than reverse loss. So this value is 1% kabatti. So A1 is greater than A1 value ante ichadu 10 ichadu.
10 ఇచ్చారు.
Yeah, 1 plus, sorry, A1 value ante ఇది 1 plus R1 by R2 value 10. This is 10. Okay, so the 10 into 100 is 1000. ఇది తీసురండి. ఇది 10 1000. Okay, A1 at this less than A1. That means A1 should be greater than 1000. Understand?
Yes, sir.
Hmm?
Yes, sir. Yes, sir.
Yes. Yeah, this is. So that with this amplifier, we can get the open loop gain. A1 is what? Open loop gain, whose value is greater than 1000 we got. Okay, got my point? Uchinda 1000. A1 is greater than 1000 వచ్చింది మనకి 1000 అంటే 10 cube. Am I correct?
Yes.
Yes. So now consider the open loop gain of CS states. CS means common source states. Okay. So whose gain formula is what? GM into RD is 10. That is open loop gain. GM into RD is 10. Suppose the same, whatever the previous example, whatever the consideration we took, that means for getting what is the value of this gain, okay, to bring the less than 1% of error. Same concept if you apply for this circuit, this is the common source stays. If you apply this is what? MOSFET amplifier. That is what? Op-amp operational. Okay. See the difference between this and that, where you can get the 1% less than 1% of gain error guaranteedly. So by choosing the A1 value, okay, greater than 1000. Am I correct? Hello. In the above problem or in the previous example, the final conclusion is to get the one less than 1 or equal to 1% of gain error. Okay, how much open loop gain should be there? We need 1000 or 10 cube. A1 open loop gain value should be 1000. Then only you can bring the less than 1% of gain error. Am I correct?
Yes, sir.
Okay, come to conclusion. Yes or no? The previous example, final conclusion is he asked about what should be the A1 value, what should be the open loop gain value to bring the gain error is less than 1%. So by the application of the procedure, where we found that if you choose the A1 value is 1000, then you would have less than 1% of gain error. Okay. So now the same concept I am going to apply for the mass amplifier. Okay, that is a CMOS, not CMOS, sorry, CS states. Here see, its open loop gain is GM into R is equal to 10. It is extremely difficult to guarantee an error of less than. So whenever you have a open loop gain is 10, then you cannot, there is no guarantee to bring the less than 1% of gain error. This is due to the, what is the problem here means, because of variations in the mobility and gate oxide thickness and transistor and resistor values. All this together, you will get at least 20% of error. You never get the less than 1% of error, gain error. Understand? Because all the variations, if you include all the variations, so then you will get greater than 20% of error. You never bring the 1% of error. Hello. So this is what MOSFET or hello, students, are you understand?
Something, sir.
Yes, sir.
Yes.
Yeah. So this is the MOSFET. What is the maximum gain? What is the gain of the MOSFETs? Beginning I told you, you can bring tens. You will get the gain in tens with single MOSFET. For BZ, with BZ you can get the hundreds of gain. But with the op amps, how much gain you will get? You can get a higher gain. 10 to 10 to yes. So that is the 10 to 10 power 5. That much of gain, that wide range of gain you will get. So that is the issue. That's why we are using the operation amplifiers, because of their higher gain amplifiers. Suppose you can understand with this, you never get the less gain error less than 1% if you use the NMOS or PMOS. What is that one? Amplifiers. Okay, CS amplifier. Yeah. So the next parameter is small signal bandwidth. What is the bandwidth? Bandwidth means the range of frequency for which our signal, the signal amplification is good, or the signal allows the input signals are presented with the output. So high frequency behavior of op-amp is very important. For what? So with the frequency variation, with the frequency of if the frequency of operation increases, the open loop gain begins to drop. Yes, you see this picture. This is the, of course, low frequency analysis. This is the frequency axis. This is the low frequencies. For low frequency, you got the faithful amplification or good gain. But as the frequency increases, your gain is decreasing like this. It's falling. It's falling. Okay. So this is the higher frequencies. This is the higher frequency. When we move to the higher frequencies, the gain drops, begins to drop, create large error in the feedback system. So gain decreases means you will get the gain error. Okay, this picture is called the gain roll off with frequency. How the gain is roll off. Roll off means decreasing with respect to the frequency. This x-axis is the 20 log gain, and y-axis is the 20 log gain, and x-axis is the frequency axis. Okay, so this is the gain is stable up to this point. So at this frequency, the gain starts to fall down. This is called the 3 dB frequency. 3 dB frequency. Small signal bandwidth is defined as the unity frequency. What is the unity frequency? Unity frequency is nothing but this FU is called the unity frequency. Yeah, this is FU. So F suffix U is called the unity frequency. So the unity frequency is the frequency at which the gain is how much? 1 dB. 1 dB. 1 dB means how can you say 1 dB means how can you show? You can show is 0 in this one. Okay. Which can be reached several gigahertz in today's CMOS op-amps. Yeah, this FU is how much? FU is how much? It is 1K or 1 mega or 1 giga something. So it is in the range of kilohertz or megahertz or gigahertz. Today you can extend this. That means if you extend means you can go up to like these points. You can extend this characteristics like this. Then FU may be a gigahertz. So that is the what unity gain frequency. So for small signal bandwidth, we need to know the what is the unity gain frequency. If the unity gain frequency is very high, then the small signal bandwidth is very high. If the unity gain frequency is very less, suppose this FU is less here suppose here is FU, then I think small signal bandwidth is small. This is called the from here to here is called the small signal bandwidth. Small signal bandwidth. If you increase like this, then the bandwidth is increases. Understand? Hello?
Yes, sir.
Yes. So the 3 dB frequency is the F3 dB. I also specified to allow the easier prediction of the closed loop frequency response. Okay. Yeah, one more problem here. In the circuit, I will show you. Assume that the op-amp is a single pole voltage amplifier. Whatever the amplifier has a single pole. Okay. If Vin is a small steps calculation, so see this is the circuit. The same circuit, earlier circuit. So non-inverting amplifier. So assume this op-amp is a single pole voltage amplifier, where Vin is the what is the input? A step input. So then calculate the time required for the output voltage to reach within 1% of the final value. Okay, that is one point. Find at what time the output can reach the input value. Okay, because step means this is the input you are giving step. So your output is starting and rising towards this input value. At what time it reaches the output value? It reaches the input value. So if you want to draw here, both are combined, then your output is coming like this, and here start to rising. Maybe this input and this output should meet at one point, at some time, but it happens after a long time, so that we cannot wait up to that time. So that we need to allow some error. That is a 1% of final value. So means at what time you can have a this much time. At what time you can, what is this time to reach your output to the input final value? That is the one we should measure. And one more thing, what unity gain bandwidth must the op-amp provide? Okay, if 1 plus R1 by R2 value is 10, if 1 plus R1 by R2 is approximately 10, okay, and settling time is less than 5 nanoseconds, what is the unity gain bandwidth that we want to find? Unity gain bandwidth means FV, okay, FV, okay, this FU, sorry, we want to find. Okay, for this is giving the values 1 plus R1 by R2 is 10 and settling time is less than 5 nanoseconds. What is the settling time? Settling time is the time required for the system to reach the output, okay, to the allowable error, okay. So, and one more thing, assume, for the simplicity, assume that the low frequency gain is far greater than unity. Yeah, these are the assumptions, okay. So I will start. This is the transfer function. You know, earlier I wrote output by input is equal to open loop gain by 1 plus R2 by R1 plus R2 into open loop gain. Okay. So then for one pole system, he said that is a one pole system. One pole system means it is looking like this. A of S is equal to, one pole system means A of S is equal to A naught by 1 plus S by omega naught. How many poles are there in the denominator here? How many poles are there in the denominator? How many roots are there in the denominator? Only one root. Only one root. Am I correct?
Yes, sir.
Yes. So that is called the one pole. There is no zeros. Only one root in the denominator. This is called the one pole system. One pole system. He said it is a one pole system. So that I took that structure. So one pole system is nothing but A of S is equal to, assume that A of S is equal to A naught by 1 plus S by omega naught. What is the A of S? What is the A of S? Hello? What is the A of S?
Transfer function.
Open loop transfer function. Okay,
Yes.
open loop gain, otherwise open loop gain.
Transfer.
Okay, open loop gain is A naught by 1 plus S by omega naught. So this is the, okay, next. Yes, next. See, after substituting A of S value in this equation, okay, then you will get, so A of S is nothing but A naught by 1 plus S by omega naught. So by 1 plus R2 by R1 plus R2 into A of S means A naught by 1 plus S by omega naught. So numerator and denominator should be divided with the R2 by 1 plus R2. Then what you will get? So then in the numerator you will get, yeah, yes. So what is that one? A of S is A naught by 1 plus S by omega naught by 1 plus, so R2 by R1 plus R2 into A of S is nothing but again A naught by 1 plus S by omega naught. This is. So numerator and denominator should be divided with the 1 plus S by omega naught. Okay. Then what happened? It comes like this. It comes like this. A naught by 1 plus R2 by R1 plus R2 into A naught plus S by omega naught. Got this one? Are you okay? This one.
Yes,
So
sir.
take this as a structure and substitute this value in place of A of S, and numerator and denominator should be divided with the 1 plus S by omega naught. Then you will get this equation. So later, yeah, I can write this like this. Once again, what is that one? I want to divide the numerator and denominator with 1 plus R2 by R1 plus R2 into A naught. I want to divide this numerator and denominator with this factor. Then what happened? A naught by this factor, 1 plus this factor, 1 plus this factor. This one, 1 minute. This factor. Then by 1, I think this is the factor. This by this means 1, yeah, plus only this is there. S by omega naught. This S by omega naught should be divided with this factor, 1 plus this one. So that 1 plus S by 1 plus R2 by R1 plus R2 into A naught into omega naught. Understand? Hello?
Yes, sir.
Sir,
Yeah. So this is now. So this is the open loop. This is the open loop TF or gain. This is the closed loop gain. So if this is the one pole system, he said this is the one pole system, he said. But after watching this closed loop transformation also, it is also one pole system. It is also one pole. See, only one root is there in the denominator. This is a DC, no S term. But in the denominator, only one S term is there. So that only one root is there. That is the one pole. Am I correct? I'm waiting for the response.
Yes, sir.
Open loop gain is one pole system, and closed loop gain also. Now we got one pole system. Am I right? Huh?
yes, sir.
Yes, sir.
Just now look at this, indicating that the closed loop amplifier is also a one pole system with a time constant equal. Time constant is tau. What is the tau value here? S by 1 plus this one is there. Okay, here generally the exact writing is something 1 by 1 plus ST. This is the structure. Here T means tau time constant. What is the in place of T here? 1 by 1 plus R2 by R1 plus R2 into A naught into omega naught. This is, understand?
Yes, sir.
The main what is the structure is 1 by 1 plus ST, or you can write 1 by 1 plus TS also. I think who is teaching control system, they know what is the TS like this. You can write every pole and zero like this, every pole like this. 1 by 1 plus TS, where T is the time constant. Time constant. In place of T here, this is in the denominator you have a 1 plus ST. In place of T, if you write the T, what is that in place of T? 1 by this whole thing. 1 by this whole thing is there. So that is the tau. Understand?
Yes, sir.
Yeah. Now, what is said?
Yes, sir.
R2 into A naught by, sorry. Yeah. So he's saying assumption is given like this. 1 minute. Yeah, this is. Low frequency gain is greater than unity. Low frequency gain is greater than unity. What is the low frequency gain here? Low frequency gain is here means this is the low frequency gain. Okay, or you can say this is. You can say this is. Okay, so this is the low frequency gain. This low frequency gain is far greater than unity. He said that as assumption. Okay. Since it's far greater than unity, this is far greater than unity. This value is far greater than unity. I think I can neglect this one. I can neglect this one. Then 1 by, what is that? R2 by R1 plus R2 into A naught omega naught. This is. I can write this as, okay, I can write this as R1 by R2, sorry, R1 plus R2, R1 plus R2 by R1. Am I correct? Yes. R1 by, yeah. So 1 by kada, 1 by into okay, R1 plus R2 by R1, R2. Yeah, R2, not R1. R2 is multiplied with A naught into omega naught. I can write this as R1 plus R2 by R2 as 1 plus R1 by R2. Okay, into one more term is there, 1 by A naught omega naught. 1 by A naught omega naught. Yeah, this is. So since this value is far greater than 1, you can neglect this one and you can write this as like this. This is called the what? Time constant. Got it? Hello?
Yes, sir.
Yeah. So next, what input you applied? Step input. Step input means you can write Vn is equal to A into U of T. A into U of T. That is a step input. A into U of T is a step input. A is the constant. So now you can apply V of T is the response with the, for the, this is the output. This is the output. Okay. So the response is the response of the system for the step input is like this. So what is that one? V out of t is equal to, yeah, input is a, constant is a, is multiplied with 1 minus gain. Gain is 1 plus R2 by R1 here. So 1 plus R1 by R2 is multiplied with 1 minus e power minus t by tau into u of t. This is the formula. So after submitting u of t and everything, input and everything, you will get the final output response for the step input is. So forget about these things. Forget about this thing. A is the constant, this is the input A, and u of t is the u of t, and the response for the response of the output for the input is 1 minus e power minus t by tau. Okay, this is the gain you got. Yes. Now, what is the final value in this equation? Final value means V final. This is the, what is the final value here? So final value means t is infinite. T is infinite. E power minus infinity value is 0. So that this term is 0. So that your final value is equal to, so A into 1 plus R1 by R2 only. Yes. Your final value is equal to how much? V final value I can write V out is equal to V final value is nothing but, after substituting the t values in infinite, okay, how much you got? A into 1 plus R1 by R2. This is the final value. Okay. So now what is saying, for 1% of settling, V out is equal to how much? 0.99 VF. Okay, is given this one, 0.99 VF. 0.99 VF means, so in the same equation, in this equation, so at t is equal to 1%, at t is equal to 1%, this is a 1%, that is equal to A into 1 plus R1 by R2, okay, 1 minus e power, this is a 1%, minus t 1% by tau into u of t. Output value is how much? This is called the 0.99 VF is given already in the problem. 0.99 VF. What is the final value you got? This is the final value. It is you got this as the final value VF. Then this VF, this VF cancels. Okay. So and what remains? 0.99 is equal to VF get cancelled. 1 minus e power minus t 1% by tau. This is the final. So you can rearrange this equation, then you will get, so e power minus t1 1% by tau is equal to 1 minus 0.99. That is equal to 0.01. Then apply log both sides to find the tau value. To find the final tau value. Hello, understand this procedure? Oh, sorry. Hello?
Yes, sir.
Yeah. So how to find the tau value? I am going to find the tau value here. So when t value substituting the infinite, then final value, then this becomes 0. Then V final is equal to A into 1 plus R1 by R2 will get. So, but he is giving t when t is equal to 1% settling time, then your output is 0.99 VF. Okay, and this A into 1 plus R1 by R2 already we can write as VF because of earlier derivation. Then VF cancel, 0.99 is equal to 1 minus e power minus t 1% by tau. You got this is. Then so bring this one this side and this side. Then 1 minus 0.9 is equal to 0.01 is equal to e power minus t 1% by tau. I want this tau value. I want this tau value only. Remaining all things are we know. So that apply log both sides. Apply ln 100 both sides. Okay. Then yeah, this is 0.99. So now this is the tau ln 100 value is that, but 4.6. It's approximately 4.6 tau its value. So he is given for 1% of settling, the tau value is 5 nanoseconds. Settling time is 5 nanoseconds. For 1% of settling, time is equal to settling time. TS you can write as 5 nanoseconds. 5 nanoseconds. TS is equal to. Okay. So for 1%, yeah, how much we got for 1% settling time? For 1%, for 1% settling time is equal to 5 settling time 5 nanoseconds. So for this, how much you got calculation? 4.6 tau is equal to 5 nanoseconds. Then tau is equal to 5 nanoseconds by 4.6. That is equal to it's maybe 1.09 nanoseconds. That is the tau value. Once you got the tau value, okay. So what is this formula? According to this formula, tau is equal to one formula we got. That is tau is equal to 1 plus R1 by R2 into 1 by omega naught A naught. This tau value we got. What is that one? 1.09. 1.09 nanoseconds is equal to this value 10 is given. 10 and omega naught value and A naught value we want. So into 1 by omega naught A naught. So from this omega naught A naught value you can get 10 by 1.09 nano is equal to 9.21 grades per second. When we convert this, its value is 1.479 gigahertz. This is the, what is the omega naught and A naught? This is nothing but small signal bandwidth. This is, understand? Hello?
Yes, sir.
Yes, sir.
So for this circuit with this all these assumptions, okay, for the given values, you got the small signal bandwidth is how much? 1.47 gigahertz. And what is the time constant you got? Time constant is 1.09 nanoseconds. See, this is the problem. What are you asking? This is the circuit has given. Is the single pole voltage amplifier is set, A of S. Then you need to find the closed loop transfer function. Then there is also open. This is also single pole transfer function. And for this amplifier, if the input is applied like this, if the input is applied step input, then the output is responding. The output is increasing towards the input. But so we need to, the output and input must be meet at some time. But how much time it takes is called the settling time. So that it generally, usually it never meet both. But if you wait long time, then you may get the less error. So that what is saying, you need to calculate the time required for the output voltage to reach within the 1% of final value. This 1% is error. Okay, so with unity gain bandwidth of op-amp is 1 plus R1 by R2 is 10 and settling time is less than 5, then find the small signal bandwidth. So with these assumptions, and you need to assume one thing, low frequency gain is greater than unity. So with this is the open loop transfer function, and single pole system is like this. So after substituting single pole system AFS value in this system, in this transfer function, then you will get the closed loop transfer function is like this. After dividing numerator denominator with this term, then you got this one. So this is the rearranging the equation to get the to count the how many number of poles and zeros are there. So no zero, only pole is again one pole is there. So this is called the tau. Okay, so this is time constant values. This is the time constant value. This time constant value is that means 1 by tau value is 1 by 1 plus R2 by R1 plus R2 into A naught into A. This is the low frequency gain. He said that is far greater than 1, so that you can neglect this. Then only this term is there. You can rearrange this term and you will get finally tau value is 1 plus R1 by R2 into 1 by A naught into omega. So now What is saying? Input is step input. So this is the V input. For the step input, the output response is, yeah, this is the output response. What is V out of t is equal to approximately equal to A into 1 plus R1 by R2 into 1 minus e power minus t by tau into U of t, of course. Okay, so whenever the final value, I want to find the final value first of all. When t is infinite, this term is becomes 1. Then V out is equal to only A into 1 plus R1 by R2. This is called the V final value. Okay, so but he's saying if you take the settling time of 5 nanoseconds, if you take the settling time 5 nanoseconds, then 1% of error is there. T is 1% of t. So that in place of t, you can substitute the 1%. Then in this equation, see, this is the 1%. At that time, V out is 0.1199 VF because of 1% error. Okay, 1% of error, its value is V out is equal to 0.11 because 100% VF minus 1% means 1 VF is equal to how much? So 0.99, sorry, 100% means 99. Okay, 0.99 VF. So that you can substitute here, VF, EF get cancelled, then rearrange this equation, apply the log both sides, then finally you got the tau value as how much? Tau value is equal to how much you got? Yeah, for 4.6 tau. T1 value is equal to 1% is equal to 4.6 tau. 4.6 tau. That is the, yeah. So that is equal to 1.09 nanoseconds. So then you can use this one, substitute to find the small signal bandwidth A0 into omega naught value. Then it's we will get the 1.479 gigahertz or 9.27 grade per seconds. Okay, got it? Hello?
Yes, sir.
Sir.
Yeah, coastal. Okay. So can I raise this one?
Noted, sir.
Okay. So you must be wait some time. Okay, I will stop this one.